soon we're going to finally formally define the Gaussian process regression model. But before we jump straight to it, to really understand what's going on, we're going to first take a look at the key step in deriving the inference equations for doing inference in a Gaussian process regression model. So up here, we sort of informally defined a Gaussian process regression model with this equation, where we said we're going to put some distribution on these y's by taking a Gaussian process at these x's and then adding some independent Gaussian noise, epsilon. And whenever we're doing regression, the thing that we're usually interested in getting our hands on is the posterior predictive distribution on some of the y's given the values of some of the others. So for example, maybe we're given the values of these y's at these x's, and then we get a new x or new x's, and we want to figure out what the posterior predictive distribution on those new y's, on the corresponding y's is. Now, the reason I wanted to factor out this key step is because doing this inference only involves multivariate Gaussians. So remember, what we were talking about in the last video is that whenever we're doing regression with Gaussian processes, we're always in the trivial case. We always only have these finitely many points, and we're looking at the distribution of these things at these finitely many points. And so it turns out that even though they call it Gaussian process regression, really it all just boils down to working with multivariate Gaussians. There's really nothing really that fancy going on here. And to really emphasize this fact, I wanted to just do this video where we derive the key part of the inference, where we only thinking about living in multivariate Gaussian land. So for this video, forget all about Gaussian processes and just think about multivariate Gaussians. Okay, so now we're in multivariate Gaussian land. We're not thinking about Gaussian processes. And we're going to let z be a normal, multivariate normal random variable with mean vector mu and covariance matrix, let's say k. And let's let z be in Rn. Now, before we were using z for a Gaussian process, but now I want to emphasize z is just a multivariate Gaussian. And let's also take another normal random variable, epsilon, with mean 0 and variance sigma squared times the identity. And let's take these two random variables to be independent. So z is independent of epsilon. Okay, and epsilon also will be in Rn. And now let's think about the sum of these two independent multivariate Gaussians. So we'll let y be their sum. And what do we know about the sum of independent multivariate Gaussians? Well, we know from before when we talked about sums of independent multivariate Gaussians that y has a multivariate Gaussian distribution. It's a Gaussian with mean equal to the sum of the means, and the covariance is the sum of the covariances. So it's mean mu covariance k plus sigma squared times I. Very nice. And so if you don't know, if you're not familiar with this fact, then you can watch in another video, we talked about this property, the sum of independent. That's in the probability videos. Sum of independent Gaussians. A very handy property. So that's nice, okay. But now we want to figure out what is the distribution on some of the coordinates of y given some of the other coordinates. So that's going to be the thing that we're going to focus on. So let's think about, let's say a is, let me put a over here. So let's say a is, say, the numbers 1 up to L, and b, let's put b over here. B is going to be L plus 1 up to n. So a is going to be the indices, and here L is going to be some number between 1 and n. A is going to be the indices of the first part of y, and b is going to be the indices of the second part. So we can break up y as ya, yb, where ya is y1 down to yl, and similarly yb is yl plus 1 down to yn. So that's y. And we can, of course, similarly, we can break up mu in a similar way, just in exactly the same way, mu a and mu b. Maybe I should write what yb is over here, just to be perfectly clear. Yl plus 1 down to yn. That's a vector. Running out of room. Sorry. Let me do that one more time. L plus 1 down to yn, this vector. I think that's clear. And similarly, we can partition mu in this way, and we can also break up, let's call this thing C. I'm going to call this matrix C, CA into these blocks. We can make a block matrix, CAA, CAB, CBA, and CBB. So CAA is the upper left L by L block of this matrix C. So CAA, well, I think you get the point. You get the point. And we can also break up K. Let's go ahead and break up K in exactly the same way. KAA, KAB, KBA, KBB. Okay, that's all good. And now our task, if we choose to accept it, is to figure out the conditional distribution on YA given YB. So we want to figure out what this is. This is the key step. Let's say little yb is some values of these variables. And so this conditional distribution, these random variables conditioned on these have some distribution. And what is it? Well, if you watched the videos, or if you're very familiar with multivariate Gaussians, or if you watched the videos on multivariate Gaussians, then you would know that in fact we derived, or we didn't prove it, but we wrote down the formula for this conditional distribution. And it is, in fact, also a Gaussian, and it has mean M and covariance matrix D, where, let's write down what M and D are. So now, do you remember the mnemonic? Do you remember the formula? I talked about a little story, a visual sort of mnemonic to remember what M and D are here. So we have this partition, and it's Ma jumped in a cab, C is the BB gun, inverts it, X the cabbie, but here it's Y instead of X, so it's X the cabbie minus gets her money back. So that's the formula for the conditional mean. Maybe that's a plus there. Plus. Very easy to remember with the mnemonic. And for the covariance matrix, it's, what is it? Think about the determinant of this. If this were just a 2 by 2, the determinant would be CAA, CBB, CA minus CAB, CBA. But that doesn't make sense, so we can move CBB over if it's a matrix, and we get CAA minus CAB, CBB inverse, CBA. Okay, that's just my little trick for remembering these formulas. And now what are these? Well, let's plug in what we know. Let's actually scoot this down a little bit so we can have space to write this one. This one is mu a. Do we know it? No, mu a is just some mu, just something we've assumed. So we have mu a CAB. What is CAB? Well, CAB is KAB, right? This was C. C is the sum of K plus this thing, which is just on the diagonal. So if we add a diagonal matrix to K, then CAB is just KAB, right? So we have, so CAB AB equals KAB. And similarly for CBA, that's just KBA. Whereas CAA, maybe I'll go ahead and put that here. CAA is KAA plus sigma squared. Maybe I'll just use I again. It's a smaller identity matrix, but we'll just put that. And similarly for CBB, it's KBB plus sigma squared I. Okay, so this is mu A plus KAB CBB, which is KBB plus sigma squared I, inverse times YB. YB is just whatever we observed, minus mu B. Very easy. And what is this one? Well, okay, so we can just plug in CAA is this, so let's plug it in. KAA plus sigma squared I minus CAB is KAB. CBB is, that was this thing, KBB plus sigma squared I inverse times CBA, which is KBA. Beautiful. So that's M. Maybe I'll just go ahead and put M and D. And let's emphasize those. Those are very nice formulas. They may look a little hairy, but the fact that we can do exactly, we can just write down these analytical expressions for this posterior distribution is a beautiful, beautiful thing. That is a very rare to be able to do in such a general model. So this is a beautiful fact. So this is the distribution of YA given YB equals little yb. It's this very nice multivariate Gaussian distribution. So that's the key step, and in the next video we're going to see how this is used, applied in the Gaussian process regression model in order to get the posterior predictive distribution. And that will actually generalize our earlier development of Bayesian linear regression. And it was so easy. I mean, that was just, we were able to just write down the formulas. No work at all. And the reason that we were able to avoid all that work that we did earlier in Bayesian linear regression is that we just used this very nice theorem about the conditional distribution on some of the coordinates of a multivariate Gaussian given the other coordinates. And that, proving this fact, is actually quite non-trivial, or at least involves quite a lot of linear algebra calculations to do. So there's nothing fundamentally different in what we're doing to derive this than what we did before for the Bayesian linear regression. Okay, so that's the key step. And let me emphasize just one more time at the point at risk of being repetitive that this did not depend in any way on Gaussian processes or properties of Gaussian processes. This is just using facts about multivariate normals. I mean, we're going to eventually use the fact that a Gaussian process has multivariate normal finite dimensional distributions, but there's no fancy math, involving Gaussian processes in general that was required to do this key step. It's all just multivariate Gaussians. All right, and next we will see Gaussian process regression.